A cool attention variant was widely adopted in many leading solutions in OpenAI's parameter golf challenge. But how does it work? In a transformer architecture, we process an input sequence with a stack of attention and feedforward network layers. Let's take a closer look. The attention layer gathers relevant context for each token. We start with a sequence of token embeddings, let's say x1 through x5. We obtain the value vectors by applying a learned linear transformation called the value matrix WV. For each token, the attention layer produces its output by computing a weighted sum combination of these value vectors. The attention weights are computed as a scaled dot product between queries and keys, followed by a softmax. We then project each attention output using the learned linear transformation, WO. This allows us to update each token's embedding to incorporate relevant contextual information gathered from the rest of the sequence using residual connections. This all sounds great. But something's off. Here, we can break down this summation into two parts. One that sums over all previous tokens, and one that captures the contribution from the current token itself. This first component contains the rich contextual information we want attention to extract. The second component captures the value from the current token itself. To see why this could be a problem, let's look at feedforward networks. The feedforward network processes each embedding independently. A typical feedforward network is a two-layer MLP. First, we pass the input vector through a linear layer, then apply a nonlinear activation function. Finally, a second linear layer maps the result back to the original dimensionality of the token embedding. As with the attention layer, we update the token embeddings using residual connections. Comparing these two processes side by side makes the issue clear. Here, the value vector Vi is computed by applying a learned linear projection to the embedding Xi using the value matrix WV. This means the Vi direction, a linear function of Xi, is already a direction the residual and FFN pathway can express. This mixing of contextual and pointwise signals in the attention output poses a problem. It forces the attention mechanism to choose between modeling contextual relationships and pointwise features, leading to unnecessary competition between the two. One potential fix is simply to ignore the current token entirely. That is, make the self-attention exclusive for capturing context. But this simple approach does not work. Two main reasons. First, value vectors within a sequence tend to be positively correlated. Similar tokens have similar value directions. Consider the sentence, "Shall we drive your car or my car?" The word car appears twice. At the start of training, both occurrences share identical embeddings, and therefore identical value vectors. Standard attention lets the second car attend heavily to the first car. So the second car absorbs the first car's value direction, even though what the first car actually needs is context from your, and the second car needs context from my. The self-value direction bleeds in and crowds out the contextual signal. Even with the weight AI set to 0, the self-value Vi direction can still leak into the attention output through nearby or semantically similar tokens. Second, preventing attention from attending to the current token can hurt performance, because it removes the flexibility to use the weight AI as an attention sink, allowing the model to avoid assigning excessive weights to irrelevant tokens. Let's take a closer look at the problem with a trained model of sequence length 2048 trained for 100 billion tokens. On the left, the average attention weight to the current token is relatively high. On the right, we see that the average cosine similarity between the attention output and each token's own value vector rises with layer depth. In other words, the attention output is heavily aligned with each token's own self-value vector direction. The paper refers to this as attention similarity bias. This bias indicates that the attention mechanism wastes its capacity modeling the pointwise feature transformation, rather than leveraging contextual information from other tokens. Therefore, the key idea is to remove the self-value vector bi from the attention output yi. This can be done with orthogonal projection. Let's visualize this process to build some intuition. Here we show 5 value vectors in 3-dimensional space. Using the attention weights computed from the query and key vectors, we scale the value vectors and sum them to form the attention output y5. To remove the self-value vector component, we need to find a vector z that is as close as possible to our attention output and is also perpendicular to the self-value vector. In other words, the vector z is orthogonal to the self-value vector. But how do we find this vector z5? Here's a key fact from linear algebra. Any vector can be decomposed into exactly 2 parts: a component in the direction of the vector v and a component perpendicular to v. These 2 parts together reconstruct y exactly. So we can always write y as z plus alpha times v, where z is perpendicular to v. If we can find the scalar value alpha, we can determine the vector z by removing the vector alpha times v from the attention output y. So, how do we actually compute the scalar value alpha? We need z to be perpendicular to v, so their dot product must be 0. Applying the linearity property of the inner product, we can break the equation into 2 parts and rearrange it as follows. By moving the norm of the vector to the denominator on the right-hand side, we obtain the precise value of alpha. Plugging the alpha into the equation yields this expression. This is the core idea behind exclusive self-attention. And the beautiful thing is that this works regardless of how the attention weights were computed. We do not need to change the query, key, or value matrices. We only need to apply this one geometric correction at the end. Now let's see what this looks like in code. Here the input x has dimensions of batch size b, sequence length t, and the embedding vector dimension d. The standard multi-head attention computation stays completely unchanged. We compute the query, key, and value vectors using the learned linear projection, and then compute the attention output y using the standard formula. The XSA mode simply adds 2 lines. First, we normalize each value vector to unit length, giving us Vn. Next, we remove from y the component that lies in the direction of Vn. That is, we subtract y's projection onto Vn from y. That is it. 2 lines of code changes. Drop this into any existing transformer, and the attention output is now guaranteed to be orthogonal to the self-value direction. As with standard attention, we compute the final output by applying the output projection matrix WO. With this change, attention can focus exclusively on what it was always supposed to do, gathering context from other tokens. But does it actually work? Let's look at the training and validation loss curves. The author tested 3 model sizes, 0.7, 1.4, and 2.7 billion parameters. In each case, XSA sits below the baseline throughout training. The margin is not dramatic, but it is a consistent improvement in all cases, and the gap does not close as training continues. But what about downstream tasks? Here is the performance across a suite of language understanding benchmarks. The improvement grows as the model gets larger. One interpretation: bigger models have more attention capacity to begin with, so freeing that capacity from redundant self-direction encoding yields larger absolute gains. But practical adoption depends on more than accuracy. Does adding XSA slow things down? Here, the paper reports the speed and peak memory usage on the different sequence lengths. Compared to standard attention, XSA introduces minimal computational overhead. The same trend holds for varying model sizes. But how robust is this to changes in hyperparameters like the learning rate? The learning rate sweep addresses this concern. Across a wide range of learning rates, XSA consistently outperforms the baseline. This matters because adding just 2 lines of code to your existing training setup can yield improvements almost for free without requiring any additional hyperparameter tuning. Furthermore, as we increase the sequence length from 512 tokens to 1024, 2048, all the way up to 16,000, the gap between XSA and the baseline grows larger. Think about why this should be true. The whole point of XSA is to help the attention layer focus on contextual information from other tokens. When your sequence is short, there is not much long-range context to gather. But as the sequence grows longer, the value of accurately integrating information from many distant positions increases. Standard attention wastes capacity by redundantly encoding each token's own information, a problem that intensifies with longer sequences. XSA eliminates this inefficiency, with benefits that grow as contextual demands increase. To sum up, 2 lines of code, no changes to the standard attention computation, and minimal compute overhead. The attention output is now orthogonal to the self-value direction, enabling attention to focus solely on contextual information. The gains hold across model sizes, learning rates, and sequence lengths. What we do not yet know is whether they persist at much larger scales. That said, this is certainly a promising direction. Thanks for watching, and I'll see you next time.